Inside any given container of gas, trillions of tiny molecules collide in a state of constant, unpredictable motion. Tracking the kinetic and potential energy of every individual particle in this space is mathematically impossible. The sheer scale of these microscopic collisions makes individual tracking a dead end for engineering. Thermodynamics solves this by zooming out. We measure macroscopic properties to define the system's state. Pressure and temperature are intensive variables, unchanged by gas amount. Volume and mass are extensive, scaling directly with the system's size. By focusing on these macroscopic state variables, we gain the ability to calculate and predict how heat will convert into mechanical work. Before we can measure energy changes, we have to establish a physical baseline, a state where the system is no longer changing. Consider two gas cylinders with different temperatures separated by a diathermic wall, allowing heat to flow. Eventually, heat flow stops as temperatures equalize. This thermal equilibrium is finalized by an adiabatic wall, perfectly insulating the systems from further energy exchange. This observation is the basis of the Zeroth Law. If two systems are each in thermal equilibrium with a third system, they are in equilibrium with each other. The Zeroth Law provides the physical justification for temperature as a measurable state variable. It ensures that a thermometer reading is a consistent reflection of a system's internal state. To calculate energy conservation, we use the first law of thermodynamics. This energy ledger shows that heat supplied to the system, Q, must equal the increase in internal energy, delta U, plus the work done by the gas, W. While internal energy depends only on the system's current state, heat and work are path functions. A gas can reach the same final temperature through different mechanical steps, but the specific amount of work extracted depends entirely on the route taken. This PV diagram translates the ledger into a visual map, with a dot marking our system's coordinates. Work occurs when pressure changes volume. On the map, extracted work is the area beneath the dot's path. Every thermodynamic process is a path drawn across this coordinate system, determining how the energy ledger balances. We can test the ledger's limits by locking specific variables, starting with volume to create an isochoric process. When the piston is bolted in place and heat is applied, the state dot on the graph moves vertically. Since the line has no horizontal width, the area under the curve is zero. No physical work is being performed. Because W is zero, 100% of the heat entering the system is converted into internal energy, raising the temperature of the gas. In an isobaric process, we lock the pressure instead. The expanding gas lifts a constant weight, and the state dot traces a horizontal line. Changing volume against constant pressure generates a measurable area of work beneath the path. By unbolting the piston and changing the path on the graph, we have successfully converted a portion of the heat into mechanical motion. More complex processes involve constraining heat transfer or temperature, such as the isothermal process. In an isothermal expansion, temperature remains constant. The cylinder expands slowly in a heat bath, replacing energy lost to work. Since internal energy doesn't change, delta U is zero. Every joule of heat added converts directly into work. Contrast this with an adiabatic process, where the cylinder is perfectly insulated and no heat is allowed to enter or escape. This rapid expansion creates a steeper curve on our graph. Because the system cannot draw in outside heat, it must consume its own internal energy to perform work, forcing the temperature to drop as the expansion occurs. Nature dictates the toll for each path. We can stabilize temperature or heat flow, but the ledger always adjusts internal energy to match. For an engine to power a machine, a single expansion isn't enough. The process must return to its starting point and repeat. By linking these isothermal and adiabatic paths together, we create a cyclic process. On our map, this appears as an enclosed loop called the Carnot cycle. Because the system returns to its exact initial pressure, volume, and temperature, the net change in internal energy for one full cycle is zero. The net work extracted by the engine is the total area enclosed within these four curves. This cycle is the mathematical foundation for converting a continuous supply of heat into repeating mechanical motion. Since the first law only requires that energy be conserved, we must ask why we cannot convert 100% of heat into work. Lord Kelvin observed that no engine can extract heat from a single reservoir and convert it entirely into work without causing changes in the environment. Rudolf Clausius further identified that heat will not spontaneously flow from a colder body to a hotter one, establishing a natural direction for energy transfer. Combined, these observations form the second law. Every engine must operate between a hot reservoir at temperature T1 and a cold reservoir at T2. To complete the cycle and return to its initial state, the engine is forced to reject a portion of energy as waste heat into the cold reservoir. Because efficiency is the ratio of work extracted to the heat absorbed, and because heat flow is proportional to absolute temperature, the maximum efficiency is defined by the ratio of these two reservoirs. This formula proves that 100% efficiency is only possible if the cold reservoir is at absolute zero. Since absolute zero cannot be reached, every real-world engine will inherently produce waste heat. The laws of thermodynamics define the limits of physical engineering. The ledger must balance, and a portion of energy will always remain as waste heat.